Back. All right, so reasoning under uncertainty we've been doing, and we started off with belief networks, and then we extended them into time, and we got Markov chains and hidden Markov models. And then we looked at adding in decision nodes and utility nodes, and we ended up with decision networks. So now what we're going to do is we're going to combine reasoning with over time with decision networks. So one way of viewing this is agents as processes. So agents get to carry out actions. So we're going to do the planning horizon. We could think about this as you carry out actions forever. So we're going to plan for an infinite horizon. We're going to plan until some stopping criteria is met, which is an indefinite horizon, or for a fixed and finite number of steps, which is a finite horizon. So the decision networks we're looking at were this finite horizon case. And now we're going to look at the other two cases. All right. So here's what we're going to do. So decision-theoretic planning is what this is about, often called. And when we talk about what an agent should do when it gets rewards, including punishments, and tries to maximize its rewards received. The actions can be stochastic, so we can't fully predict the outcome of an action. So we can have stochastic actions. And there is a model, however. There's a model that specifies the probabilistic outcome of actions and the reward. So we're going to assume we have a model. Okay, and we're also going to assume that the world is fully observable. Okay, we can actually observe the state of the world. That turns out to make this much easier, like in a Markov chain, or we could actually observe the state of the world. Okay, so in terms of our initial assumptions, we're going to assume an indefinite and finite stage. We're going to assume stochastic dynamics, and we're going to allow complex preferences. Okay, we're now fully observable. Remember, before, for decision networks, we were partially observable, but we're only finite stage. Okay. So first thing to think about is how utility combines with time, right? Would you prefer $1,000 today or $1,000 next year, right? Just think about what you might prefer. You know, what price would you pay now to have an eternity of happiness, right? It's a trade-off between our utility, our rewards now, and rewards in the future. So how can we trade off pleasures of today with pleasures of the future? And people take this seriously as to how to actually go about modeling the future. So think about this. So think about this question about utility and time. So how would you compare the following sequences of rewards? I get $1 million now, and then I get zero for the rest of my life. Or I get $1,000 a week for the rest of my life. Or I get $1,000 now, and then I get zero for the rest of my life. I get $1 for a week for the rest of my life. Or I get $1 this week, and $2 next week, and $3 the third week, and $4 the fourth week, and $5 the fifth week, and so on. What would you prefer? So it seems like there's some of them which are easy to compare and some of which are more difficult to compare. Okay. So now we're going to assume that the agent receives a sequence of rewards, which we're going to write as little r1 to r2 in time. And the question is, how should we assign a utility to this? Because we're going to use decision theory. It's based on utility. And what we're going to do is we're going to use the word return, or often the word value. So they're both used. Okay. So now we're going to think about the two obvious ways of doing it. One is the total reward, which is going to sum up all the rewards. And one is the average reward. We're going to get the average over the first n steps divided by n, and we're going to take the limit as n approaches infinity. How do these differ? Well, you've got to ask the question of what happens if the agent goes on forever. If the agent stops after a finite amount of time, they're not really different because they're just a constant difference away from them. However, if the agent goes on forever, they can be very different. If an agent gets stuck in absorbing world, so it dies, for example, right? The average reward is always what? What's the total reward? But what if the agent goes on forever and keeps receiving rewards? What happens with the average reward? Okay, just think about that before class. Okay, another way to do it that's very common and that we're going to adopt is, suppose an agent receives a sequence of rewards in time. This discounted reward says there's some discount factor between 0 and 1 that says you get R1 plus the discount of R, so that's 1 time steps you get a discount of gamma, and in 2 time steps you get a discount of gamma squared, and then gamma cubed, and so on. Okay, so you get this discount factor. The discount factor is between 0 and 1. If it's equal to 1, then it's just the sum of all rewards. If it's 0, we ignore all the future. We're only worrying at any time about the immediate reward. So this talks about how to trade off immediate rewards plus future. Okay, so this one here we can write, so this discount reward is R is equal to, V is equal to R1 plus gamma of R2 plus gamma of R3. And what I can do is I can pull the gamma out of this. So all of these on the right-hand side contain gamma, so I can pull it out. So that's R1 plus gamma of R2 plus, and notice this formula is exactly the same form as the one above it, right? So if we do V of t is the value obtained from step of t, we find that V of t is the reward at time t plus gamma times V of t plus 1. So this is the property of our discounted reward, okay? And so it really is asking the question, how is the infinite future compared to the immediate rewards? And we can analyze that. So it turns out that if you sum up this infinite sequence, 1 plus gamma squared plus gamma cubed, you get 1 over 1 minus gamma. If gamma is 0.9, then this is 1 over 1 minus 0.9, which is 10. Okay. If gamma is 0.99, you get 1 over 1 minus 0.99, you get 100. So what that means is that the value at any time is somewhere between the minimum reward divided by 1 minus gamma and the maximum reward divided by 1 minus gamma. And the other thing we can do is, if you just think about the first k terms and you want to get the error in the value minus the first k terms, well, that's equal to gamma to the k times v of k minus 1. So the error drops down exponentially with k. So if you just treat the first k term, we're going to approximate it with the first k terms, the error is going to drop down exponentially fast. Okay, so it's useful to know. All right. So now what we're going to do is we're going to view the world is combined utilities and rewards. That is combined rewards with a Markov chain. So the world state is information that the state knew the world state. No information about the past is relevant to the future. This is the Markovian assumption. We've done it before. We looked at Markov chains and hidden Markov models and so on. And so what this means is that if SI is the state at time I and AI is the action at time I, the probability of this SI of S of t plus 1 only depends on these last ones. So it's equal to the probability of S of t plus 1 given S of t and A of t. And so we're going to write this thing. The probability of S prime is the probability the agent will be in the state S prime immediately after doing action A in state S. And we're going to assume it's what we called stationary. That's what we did it before, is that it doesn't depend on the time. So distribution is the same at every time point. So we're going to assume this. So we're going to draw it in this format here of the same way we did before. Okay, so under this you can see S0, S1, S2, S3 is a Markov chain, but the state depends on the previous action, just like we did when we did localization. What happens is that we have the action, what information is available when we do the action, what's the previous state. We're assuming we get to observe the previous state when we do this. And then we're going to have the rewards are a function of the state and the action. Okay, and it just continues on indefinitely to the right. So now we know, because we can know what a decision network is, we know how to interpret this. The only weird thing is we have these lots of rewards now instead of just one utility. Okay, so Markov decision process, or just an MDP, consists of a set of states and a set of actions, just like we did before with the Markov chain. Set of states and a set of actions. We're going to have this probability distribution, the probability of S of t plus 1 given S of t and A of t specifies the dynamics. And we're going to have the reward as a function of S and t and A and t gives the expected reward at time t. So we're going to do big R of a particular state and a particular action is the expected reward of doing action A in state S. So then we're going to have rewards in our function of the state and the action. And we're also going to have a discount factor. So we're going to assume a discounted model here. All right, so here's an example. So each week, Sam has to decide whether to exercise or not. And there are two states. Sam can be fit or unfit. And the actions are Sam can exercise or relax. Okay, it's a good decision people have to make, whether we should exercise. And the dynamics we're going to assume is if you start off as fit and you exercise, then it's very likely you're going to remain fit. Maybe you might get injured and stop being fit. But if you're fit and you relax, well, there's a 0.7 chance that you end up as you still end up as fit. If you're unfit and you exercise, well, it's pretty hard to get to be fit. So there's a 0.2 chance. And if you're unfit and you relax, there's no chance of being fit. So there's my dynamics that I'm going to assume. Okay. And now we're going to have the reward function. So the other part of this in MDP is the reward function. And we're going to assume that it's better to be fit than unfit. So the reward's much higher if you're fit and unfit. But it's always better to relax than it is to exercise. So the worst thing is to be unfit and to exercise. That is reward of 0. The best thing to do is to be fit and relax, which is a reward of 10. Now, of course, the challenge here is that it's always better to relax than it is to exercise, but it's better to be unfit. It's better to be fit than unfit, but relaxing makes you unfit, right? So you've got to work out what's the best thing to do. So if I'm only thinking about the immediate future, then it's always better to relax. If I just have one step, but if I'm looking at the future, then maybe it's better to exercise in order to get this higher reward in the future, even though I'm going to only get this 8. Okay, there's an example. Here's another example of a simple grid world. So we have an agent is in one of these positions. There are 100 states here. The agent is one of these 100 states. The actions are to go up, down, left, and right. But these are stochastic in the example I'm going to show in a minute. So the agent actually goes in the direction it tries to go with it, probability 0.7, otherwise it's 0.1 in each of the other 3 directions. So it's an agent at this position and tries to go up. It goes up here with 0.7, it goes here with 0.1, goes down here with 0.1, and over here with 0.1. If it tries to go to the right, if the action is to go right, then it ends up here with probability 0.7. Okay, and the reward structure is here such that if it crashes into the outside, it gets a reward of -1. If it's in one of these other states, if it's on one of these grade states, then it gets the reward when it leaves. So if it's in this state and leaves, it gets a -10. If it's in this state here, so it gets, yes, if it's in this state here and leaves, it gets -10. If it's in this state here and leaves, it gets a +10. So this is a good state to be in because you get a +10. This is a bad state to be in because you get a -1. It's bad to crash into the walls. Okay, I'll just leave this. This is just what I said there. So, and now we're going to look at planning horizons. The planning horizon is how far ahead the planner looks to make a decision. So one variant of this, the robot gets flung to one of the corners after leaving these rewarding positions. So this never stops, and it has it's called infinite horizon. So we're planning to go on forever. The other one here is the agent gets a +10 or a +3 in the state and stays there getting no reward. And these are called absorbing states. So it effectively gets the +10 and stops. So the maximum it can ever get is +10. So the robot will eventually reach an absorbing state and it's eventually going to stop. And this is what's called an indefinite horizon. So no matter what it does, there's chances of landing in the probability of not hitting absorbing state ends up as 0 as time goes to infinity. So the question now is there are 2 different sorts of models that we're going to do. And the question is what information is available and the agent gets to decide what to do. There's a fully observable Markov decision process where the agent gets to observe the state when deciding on the actions. The agent gets to observe the state. And then there's a partially observable Markov decision process. The agent is a noisy sensor of the state. So it's essentially a mix of the hidden Markov model and the Markov decision process. So it needs to remember some function of its sensing and action history, because it could be like a hidden Markov model and have a belief of a probability distribution over its state, but then it needs a function of its probability distribution. That's hard to represent. So we're only going to consider fully observable Markov decision processes here. And POM-DPs are much harder to solve. So the state of the art's, solving exactly for a few thousand states. So now we're going to have a policy. So the other part we need here is a policy. Basically, it's the same definition as before, but we're going to have a policy as a function from now it's just a function of given a state, what action should it do? So remember that the states were the parents of the decision nodes, were the action nodes, and so a policy is just a function of a state into actions. So given a state S, pi of S specify what the agent who's following pi will do. Okay, and an optimal policy is one with a maximum expected discounted reward. So assuming this discounted reward policy, which we did earlier on. So it turns out for fully observable Markov decision processes, if the stationary dynamics and rewards, and if there's an infinite or indefinite horizon, there's always an optimal stationary policy. Turns out if there's only a finite horizon, there's not an optimal stationary policy. If you think about the exercising one, the last step, it's always better to relax because there's no point in thinking about the future at the last step. But if you think things are going to go on forever, it turns out there's actually an optimal stationary policy, one that does not depend on time. So here's the think about. So here's the example we'll think about in class. So each week, Sam has to decide whether to exercise or not. So the states are either fit or unfit, and the actions are either exercise or relax. So how many stationary policies are there? What are the stationary policies? Now for the grid world with 100 states and 4 actions, how many stationary policies are there? Okay, think about that. All right. So now what we're going to do is we're going to talk about the value of a policy. Now there's 2 functions we're going to define. So given a policy pi, we're going to define Q of pi is a function of both the state and the action, where A is an action, S in the state, is the expected value of doing A in state S, then following the policy pi. So I'm going to get the future reward. So I'm going to have the policy, which is going to specify what to do, but I'm going to do action A. So the agent is in state S, it's going to do action A, then it's going to follow the policy. And that has a particular reward. Has a particular expected value if the agent follows that. Because once you've done this, once you've specified the policy, it's just a Markov chain. Okay? So once given a policy, it's just a Markov chain, and now we're going to do A, then we're going to follow pi. Okay, and then we're going to have this V pi of S, where S is the state, is the expected value of following the policy in the state of S. And it turns out that these two can be defined mutually recursively. So V pi of S and Q pi of S. If you think about what these are, well, V pi of S is, well, what are you going to, you have to specify, it's sort of the same as Q, but the action is going to be just follow the policy. So that's what this says. It's a Q of following the policy. Okay, so that was pretty straightforward. And now Q of S and A, well, we're going to have to, we're going to need to, we're going to think about, well, we're going to do A. So what happens? Well, if we do A, we first of all get the reward of carrying out state in action A. And then we have to do this expectation. So there's this discount factor. And then there's the expected value depending on the resulting state. So this is exactly what we did before when we did, we're marginalizing out, we're just summing out a variable. So this is summing out a variable. So this is just summing out the previous state. So this is effectively the same algorithm that we did for decision networks. Okay, so that's what's going on here. So there's the There's the future state, there's the expected future value. We've got to discount it and add the immediate reward. Okay. So now so this was given a policy pi. Now let's look at the optimal policy. This is the star here. So Q star is, where A is an action, S is a state, is the expected value of doing A in state S, then following the optimal policy. Okay, so it's following the optimal policy after doing A. Okay, I'm going to define V star of S as the expected value following the optimal policy in state S. Well, it turns out we can again define these mutually recursively. And it turns out that Q of S of A is exactly the same thing before, which is the reward of S and A plus this discounted thing. The only difference between the previous one is we're now going to follow the optimal policy after doing A. So it's V star of S. Okay. Well, if you think about what V star of S is, well, V star of S is, well, we want the action that has the highest value, right? So we're going to just choose the maximum value for A of Q of S and A. So that's the best thing. We're going to choose the best thing to action. And that's what the pi says. It's the argument of the best actions is going to be the action. Okay, so that's basically the same definition as before, and it's really the same algorithm we did for, this is just marginalization. This is just what happened when we had to sum out this variable, this future state, and now we get to choose these two things. We get to choose both the decision function, which is this, and the new factor, which is the new V. Okay, and now here's an algorithm. We're just going to go run through this, just basically go backwards through time, and we're going to try to work out what's going on. We're just going to keep repeating this. So we're going to let VK be what's called, we're going to look K steps ahead, value and Q functions. So given an estimate of the K step look ahead function, we're going to determine the K plus 1 step look ahead function. Okay, so we're going to set V0 arbitrarily, and then we're going to compute the following one from the Q of I plus 1 from V of I. Okay, and all we're doing is just using this formulation, right? This is how to compute, given the V of I, this is how to compute Q of I plus 1, and this is V of I plus 1. Just that formula. And it turns out this converges exponentially fast to the optimal value function. So let's have a look at an example of this. So here is the grid world we did before. So here's my 10 by 10 grid, and we'll explain what these stars mean. And the bottom left here is the value function. So they're all 0 at the moment. Okay, so they're all 0 at the moment. Let's make that slightly bigger. Okay, and now what we're going to do is we're going to do one step of value iteration. So what happens here is at this point here, if you're in this position here, it's worth 10, so you get a reward of 10. So looking at one step ahead, you immediately get a reward of 10. Here you get a reward of minus 10. Here you get a reward of minus 5, and here you get a reward in here of 3. These values here, if you went to the right, you'd crash into the wall and get a reward of minus 1. If you go left, up, and down, then you end up with a 0.1 chance of getting a minus 1. So the expected value is minus 0.1. And the arrows here point to what the optimal policy is, to the policy that's maximum. Here there are 3 things, all of which are the maximum. So if I step again, let's look at what happens in this corner here. So if I step again, if I go right here with probability 0.7, I get a 10, but it's only going to be worth, it's not worth that much to me now because I've got to discount it. So here's the discount factor of 0.9. So if I step that, I get 6.3. So the optimal policy here is to go right. So go right here with probability 0.7, I end up with a reward of 10, which was the previous one. And then I discount it and I get 6.3. Okay, so it's exactly the same thing before. There's just 100 states here, but that's okay. And then we go backwards and we go backwards again and we keep just going backwards. And if I do it a number of times, eventually it finds a policy about what to do here. And I keep going backwards. I don't know how many times I've gone, maybe 20 times or something. or 30 times. And after a while, it actually converges to something, right? And it tells me what the optimal policy is here. So if I'm at this point here, I want to go down and around. And I try and go to here. This is the optimal policy, is to go here. Now if I'm notice that this is the rewarding state here, but it's not very worthwhile. It's actually more worthwhile to go, if you're at this point here, to go along here and down and to go towards this big reward. This one has a higher expected utility of 13.1 because what happens is after you leave here, the agent gets flung to one of these four corners, and they will have some value to it. That's why this is positive. Okay, so all we did here was just to go, he's looking the immediate reward, and then one step ahead, value function, and we're looking 2 steps ahead here, and now we're looking 3 steps ahead. Okay, all right. And this converges to the optimal value function, just like with the example there. And this error reduces proportional to this. That's what we did early on in here. Here's another algorithm. So it turns out the agent doesn't need to sweep through all the states. You can update the value functions for each state individually. You can do them separately. And this converges to the optimal value function if each state and each action are visited infinitely often. So you can't just sort of not explore this. You can't just sort of ignore some states. But as long as we do this, we can update our value function arbitrarily. Right? And we can either store the value function or the Q function. Okay. So here's one algorithm. Is we're going to repeat forever. We're going to select a state and we're going to update V of S. Well, what's V of S? Well, V of S is, we're going to select the state. So now we want to go back to here. We select the state and we're now going to replace the maximum over A of this thing, right? So it's the value we're storing. We're going to put everything into here. We're just going to replace this Q of A with its definition. Okay, so that's what's going on here. So that's what here. This is just Q, right? And now because we're only storing V's. Okay, and you can keep going. Okay, you can repeat forever, select a state, and just update this reward. So this together actually converges, just like the other one did. It turns out it converges faster than if we do something sensible than the other one that swept through all the states. There's another algorithm, so we could just store Q instead. So instead of going back to there, we could actually replace the other one. It says we get the immediate reward plus the discounted plus the expectation, and this one is the future state. Okay, and we can do this for an arbitrary state in action. So what we can do is, and this is what's called reinforcement learning, is we could take the S and the A they're actually doing, this particular state and this particular action, we can actually update this. So reinforcement learning, we typically learn the Q function. Okay, and that's and then we're going to update that. And if I know the Q function, I know what to do. Okay, so let's stop there. Thank you all.